Let us look at proposition number 11 of book 4 of Euclid's Elements. The proposition talks of constructing a equilateral and equiangular pentagon inside a circle. So we are given a circle, we have to draw a regular pentagon. Regular pentagon means all the interior angles are equal to each other and all the sides are equal, and there are 5 sides. This is going to be a very hectic kind of construction. What we are going to do is use the previous proposition to create a triangle, an isosceles triangle whose equal angles are double the third angle. Let's take a line segment. It doesn't matter how long or how short this is. Since we have already done it in previous proposition, I'll just keep doing it. Try to recollect what I'm doing based on the previous proposition. So we have got the required triangle. So now let's hide all this. So now here, this angle is equal to this angle because it is an isosceles triangle that we have constructed, and it is double this angle. This triangle, we have to inscribe it in this circle. So first let's get rid of this pentagon that we have already drawn, because that is what we have to construct. Okay, so let's take a random point. It doesn't matter where it is. Random point on the circle. And now we have to inscribe this triangle inside this circle. An equiangular triangle, equiangular to FGH. Okay, we know how to do this also. We have done it in one of our previous propositions. So let's begin. Let's draw a line perpendicular to the line joining the center with J. Okay, let's mark 2 points on this tangent. Now we copy one of these angles here on JK and another angle on JL. Again, we know how to do this based on our previous propositions. So circle, intersect, circle, intersect, and join those points. Mark the intersection of this ray with this circle. So now we have copied one of the angles here. Okay, let's get rid of all this that is not required. Now let's again copy the second angle. Circle, circle, intersect, circle, point of intersection, and line joining J and Q, and then intersection with the circle. Again, let's get rid of this. Now we just joined R, O. Now let's get rid of those lines, rays. So we have got a triangle which is equiangular with this with this constructed triangle, inscribing it in the circle. Okay, just to make sure that ideally we should not look at that. So basically, these are the 3 angles here, 36, 72, 72. Yes, so we have got the required triangle. Remember, in Euclid's Elements, we don't have angles, measurement of these angles. Okay, this is only for your reference. Okay, now what do we do? Now we bisect angle OJR and we bisect ROJ. We bisect this angle and this angle. Remember, this is 72 degree. So if we bisect it, we will get 36, 36. So let's bisect it. So we draw a circle, intersection, intersection, circle, circle, line joining those intersection points. Yes, so we have got this line. So let's hide off all these. Okay, we have bisected angle OJR. Now let's bisect angle O and the line joining the intersections. Okay, now let's mark the points of intersection of the circle with these two lines, bisecting lines. And let's get rid of these and circles. And let's join OW and JZ or JZ. Let's join all these points to each other. Not all of them, but so that we construct the pentagon. So OZ, RZ, RW, WJ. So we have constructed the pentagon, required pentagon. This tangent also we don't require it now. Since we have constructed it, now we have to prove that it is actually a pentagon. Now to prove that it is a pentagon, remember we have to show that all these interior angles are equal. And we have to prove that all these sides are equal. So if we are able to prove that, then we will be able to say confidently that this is a regular pentagon. Okay, for the proof purpose, we also join WO, J, Z. So that is the construction part. Now we have to prove that this pentagon is equiangular and equilateral. Equiangular means all the interior angles are equal to each other. Equilateral means all the sides are equal. So let's see how we can prove that. Remember, angle OJR and ROJ are equal to each other and they are twice this angle. Angle JRO, but JZ and OW bisect these angles. That means they cut it into two equal halves. So that means all these angles are equal. Now, in one of our previous propositions, we have seen that equal angles stand on equal circular segments. Yes. That means the segment, circular segment, WR, on that, this angle is standing. On this circular arc, this angle is standing. On this circular arc, this angle is standing. So, which means that all the circular segments are equal to each other. And based on another proposition, we know that line segments which cut a circle into segments. So, if those circular segments are equal, then these line segments will also be equal. So, that means RZ, ZO, OJ, JW and RW, they are all equal to each other. So that takes care of the first part, that is all the sides are of equal lengths. Now we have to show that all these angles are equal to each other. Now we have already shown that these circular segments are equal. So let's take two of these circular segments. Let's say RW we know is equal to ZW. Now to this equality, let's add WJO, RW circular segment and ZO circular segment. They are equal. So we add this circular segment WJO to these two segments. Then what do we get? We get RWJO is equal to ZOJW. Means this segment is equal to this segment. Again, we know that angles standing on equal segments are equal to each other. So that means RZO, this angle stands on this circular segment, RWJO. That would be equal to WRZ. Why? Because that stands on ZOJW. So that means angle RZO. So let's mark that is equal to WRZ. Now we can repeat the same logic for all the other angles, and we will end up with a situation where we can say that all these interior angles are equal to each other. So we have shown that this pentagon is equiangular and equilateral. That means it is a regular pentagon which has been inscribed on a given circle. And here, remember, it doesn't really matter where you choose the initial point. J is the initial point. I can move J, but we can't really move any other because those are based on intersections. So you can choose any point as the starting. So that was proposition number 11 of book 4 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it. And if you think somebody else can benefit from it, please do share it. That's it for now. Bye.